Good morning, students. Today we are talking about the electric potential due to a point charge. Electric potential due to a point charge. Electric potential, we know that it is the amount of work done in bringing a unit positive charge from infinity to a point closer to the source charge. Now, this is your source charge Q producing an electric field, and this is the test charge having a magnitude of plus 1. We are bringing it from infinity to a distance of r. That means we are finding the potential at point r. Now arbitrarily it is suppose at a distance of x, and we are displacing it to a distance of dx, a very small distance, and we'll be calculating the work done for the small displacement dx, and then we are going to integrate it so that we can calculate the work done from infinity to that point charge. Now, for work done, we know that the work done is equal to force into displacement. But for that, we need to calculate the force. So, what is force? Force between the two charged particle. Two charged particle is Coulomb's law. So, F is equal to Q1, Q2 upon R square and 1 upon 4 pi epsilon naught. So, Q2 is 1. So, the force will be 1 upon 4 pi epsilon naught Q upon R square. But the problem is that since both are positive, and that means the force will be a repulsive force. But this is your charge and this is your test charge. The force will be repulsive, for charge particle will be moving away from the source charge, but we have to bring this charge particle closer to the source charge. That means force is in this direction and displacement is in this direction. So angle between these two vectors is of 180. That means when we are going to calculate the work done is equal to force dot product dx, that is f dx cos theta. Theta is 180, cos 180 is 1, that is minus 1. So it will be small work done will be minus f dx. So f, the value of f, already we have calculated 1 upon 4 pi epsilon or q upon r square. So substituting the value of f, we'll get this thing. Now this is the small work done in displacing the charged particle by a distance of dx. So now what we have to do, we have to integrate it. What is integration? Means that summation. Okay, for the continuous value we integrate it. Now when we are integrating this small work done from infinity to distance r, so we'll get this thing. Now q 4 pi epsilon naught, these are the constant quantities, they will come out of the integration sign and we are left with x raised to power minus 2. Now the formula for x raised to power n integration is x raised to power n dx is equal to x n plus 1 divided by n plus 1. So what we have, we'll get x raised to power minus 2 here. So minus q 4 pi epsilon naught, this is the constant value, x raised to minus 2 integration will be x raised to power minus 1 divided by minus 1. Now that means if we take minus 1 also outside, what we'll get? We'll get q upon 4 pi epsilon naught 1 upon x infinity to r. Now substituting the value, first the upper limit, so instead of x we'll be writing the upper limit, that is r, and instead of second time, instead of infinity, will be, instead of x we'll be writing the infinity, so 1 upon r minus 1 upon infinity. But what is 1 upon infinity? That is 0, so it is 1 upon 4 pi epsilon naught q upon r. So potential will be this. Now this potential is depending upon that q, that is directly proportional to the charge and inversely proportional to the r. More the charge, more will be the potential. More the distance, less will be the potential. And look here, the value is coming out to be positive. That means for a positive charge, the electric potential is positive. Whenever there is a repulsion between the two charges, then the potential come out to be positive, and if Q will be negative, then the test charge is always positive, so there will be a force of attraction and the potential come out to be negative. Now remember that in the gravitational potential also the value comes out to be negative because that is an attractive force. Now we'll have to draw the graph because the graphs are very important. In the exam they are asking the graphs, and in the competition also they will be asking for the graph. So when we draw the graph of potential with time for a positive value, it comes out to be like this. V is directly proportional to 1 upon R. Since V is positive, so it will be in the first quadrant. Now when Q is negative, and again we draw the same graph, we know that when Q is negative, the potential will come out to be negative, so it will be in the fourth quadrant. And since V is inversely proportional to R, always remember that when first quantity is directly proportional to second quantity, the graph come out to be a straight line. If first quantity is inversely proportional to second, the graph come out to be like this. Next, if we draw the graph between V and 1 upon R, V is directly proportional to 1 upon R. That means a linear relation. So when charge is positive, V will be positive, it will be directly proportional. So when Q is negative, V and 1 upon R, because again this relation they are directly proportional to 1 upon R. We have taken 1 upon R as a physical quantity, so it will come out to be in fourth quadrant. So electric potential due to a single charge spherical symmetry, as the value of electric potential due to the charge is same at all point distance r around the charge, means when the r is constant, then V will remain as constant.